Number 48, integrated concepts. Space debris left from old satellites and their launchers is becoming a hazard to other satellites. Letter A, calculate the speed of a satellite in an orbit 900 kilometers above the Earth's surface. All right, so here we have the Earth right here in black. Okay, and we have a certain satellite in orbit that is 900 kilometers above the surface of the Earth. Okay, and what we need to do is we need to find the speed of such a satellite. Okay, so what I'll begin with, and I've done a problem very similar to this a couple of times now, and you can check out some of the numbers in the 30s here. They're very, very similar, so I'm probably just going to breeze through this part. So let's start with the formula that the force is equal to mass, right, multiplied by acceleration. So let's talk about the satellite specifically, okay? So the centripetal force, meaning the force pointing towards the center, okay, on the satellite here will equal the mass then of the satellite itself multiplied by the acceleration of this satellite towards the center, okay? Now realize that the force, in order to keep it on a circular orbit, it's a force towards the center, and the acceleration is also towards the center of the orbit. Therefore, these are really right, centripetal force and centripetal acceleration. Okay, now let's also take a look at this formula over here on the right-hand side. Now remember that this formula says that the force, gravitational force, right between two objects is equal to the gravitational constant multiplied by the mass of one, the mass of the other, all divided by the distance between them squared. Now here's the thing, right? The gravitational force between them, all right, is the same as the centripetal force, right, that the satellite experiences. It's a force of attraction. It's the inward force. That is the force of gravity. So since these two items are the same, I can also set these equal to one another, right? So why don't we do that? So we have now the mass of the, I don't know why did I put an M here? I'm just looking back. I don't even know what I said before, but whatever I said, just make sure this is the mass of the satellite, okay? So the mass of the satellite multiplied by the acceleration of the satellite, remember, that is the centripetal acceleration, will equal then the gravitational constant multiplied by the mass of the satellite, that's one object in this system, multiplied then by the mass of the Earth, that's the other object in the system, all divided by the distance between them squared. Okay? So now what do we notice? We notice that these masses can cancel, right? The mass of the satellite, who cares? It doesn't matter, it cancels. So that's great, but remember now, we want to find the speed of the satellite, meaning the linear speed. Okay, so I'm thinking, well, I don't have linear speed in here. I'm trying to figure out what variable relates to linear speed, and I'm thinking, well, I do know a relationship between centripetal acceleration and linear velocity, right, via this equation. So actually what I'm going to look to do now is take that equation, this result, and plug it in for AC. All right, so now that becomes, let's rewrite this. So now this is the velocity of the satellite squared divided by the radius right between the two objects is equal to the gravitational constant multiplied by the mass of the Earth, all divided by the radius squared. But what do you notice happens to the radius? Well, this cancels, and it cancels one of those, right? So now this equation simplifies to basically be this, right? The velocity of the satellite squared equals the gravitational constant multiplied by the mass of the Earth, all divided by the radius between them, right? And then I just have to take the square root of both sides, okay? So instead of rewriting this again, let's just get rid of that. Take the, well, oops, not the square root of that side, but square root of that side, okay? So this will be now the formula, all right? So literally all I have to do now is plug some stuff in. So this is for letter A. So let's just plug it all in. So the velocity of the satellite here will be equal to the square root of the gravitational constant, which is 6.673 times 10 to the minus 11, right? Multiplied then by the mass of the Earth, which is over here, right? I don't know if you have to memorize it, but you probably should be doing enough practice where just being memorized by virtue of doing the problems. And that is all divided by then the radius between them. So now the radius between them, you have to take the center of mass of the Earth into account. Okay, so it's not 900 kilometers. All right, it's really the total distance between these two, from the center of the Earth to really the center of the satellite. But I guess the assumption is that this radius in here is negligible. Most likely it is. I mean, we're talking about, millions of meters. All right, so this is probably a few meters, negligible. So what I need to do really is in order to figure out the appropriate distance, I got to add these two, right? I got to add the radius of the Earth to the distance above the Earth that satellite is. All right, so let's do that. So 6.38 times 10 to the 6th. Okay, and don't worry, I hear you. You're saying, wait a minute, you can't add them. This is kilometers. You're right. We can't add them, right, in this form, okay, because this is in meter, this is in kilometer. But all I'm going to do is add, 3 zeros to the end of this, okay? Well, you can just multiply it by 1,000 too. It doesn't matter. So this becomes 900,000. All right, and let's just calculate. All right, so take the square root of 6.673 times 10 to the minus 11 multiplied by 5.97 times 10 to the 24th and divide that all by, realize something, no, it's not squared anymore, sorry. I'm so used to doing this formula with it r being squared, and I just realized as I'm looking, I'm like, oh wait, it's not squared, but it shouldn't be because one of the radii were canceled, okay? So divided by, let's get back on track, 6.38 times 10 to the 6th plus 900,000, close parentheses, and we get a value of about 7.4. All right, 7.4 times 10 raised to the third, times 10 raised to the third, and that is in meters per second. All right, so this is the velocity of the satellite, okay? Great. Why don't we take a look at letter B? So suppose a loose rivet is in an orbit of the same radius that intersects the satellite's orbit at an angle of 90 degrees relative to the Earth. Okay, what is the velocity of the rivet relative to the satellite just before striking it? Joy, right? There's a lot of stuff going on here, a lot of relative to this and relative to that. It's a good question, though. I'm not saying it's a bad question, but there's just a lot to consider. So first things first, what, in terms of my picture here, where would this thing be? Well, you notice how this satellite here is, orbiting in this plane, right? A rivet now is orbiting with this same radius, okay, but in a 90-degree orientation to the satellite. So it might look sometimes, it's hard to represent this on a two-dimensional, screen here, but it would be something like this, like the rivet would have an orbit like this, in this direction, okay, around the Earth, right? Something like this. All right, and it would intersect right here. So pretend that, this part I just drew in red should be three-dimensional, all right? So, okay, so hopefully that should make a little sense. Now, let me just get rid of that. Just keep that in mind, okay? So, well, actually, let me not get rid of it yet. One thing now, okay? So you might say, well, wait, don't we have to now find the velocity, right, of this rivet in order to figure out, how, in order to figure out, how fast the collision is relative to the satellite? And you're right, we do. But notice what we did already. We already found the velocity of the satellite. And when we found the velocity of the satellite over here, what did we realize? What units and values did we use? All we did was we used the radius between them, the mass of the Earth, and this is constant. So literally there's no difference, right, in terms of calculating, the velocity for this rivet in this red orbit here, as opposed to calculating the velocity of the satellite. Because look, the masses would have canceled in both cases. So what can I say? That the mass of the, that the velocity of the rivet relative to the Earth should be the same. Okay? Now, since we're talking about relative velocities here, I have to be very specific and careful with what I'm talking about. So let's write down a couple of things. So the velocity, so what did we find over here, in terms of relative velocity? What we found is we found the velocity of the satellite relative to the Earth, and that was equal to 7.4 times 10 to the 3 meters per second. Now, we just discussed, right, the velocity of the rivet relative to the Earth should be the same exact value, okay, of 7.4 times 10 to the third meters per second. Okay, so that should make sense. But now, what's the question asking me? The question is asking me to find the velocity of the rivet relative to the satellite. So I have to find this, the velocity of the rivet relative to the satellite. Now, we've done a lot of examples about relative velocities back in Chapter 3. So if this is a little rusty, please, look back to some of the Chapter 3 questions, all right? And so this is our question. Now, knowing it's a relative velocity question, it makes me think of the relative velocity formula. So what is that? The relative velocity formula is this. The velocity of A relative to B should equal to the velocity of A relative to C. No, actually, well, I can put it however but you'll see the definition back like this. Velocity of A relative to C is equal to the velocity of A. No, what am I doing? I was right the first time, right? So you should always stick with your first instincts. The velocity of A relative to B is equal to the velocity of A relative to C plus the velocity of C relative to A. Now these, as long as you have the right order, it doesn't matter what A, B, and C is, all right? But I'm just a little particular. I want to make it consistent to what we were doing before. So now A, B, C can be anything. So let me frame it this way now. So it's the velocity. So what do I want to find here? I want to find the velocity of the rivet relative to the satellite. So that better equal the velocity of the rivet relative to the third object in the problem. Well, that's the Earth, relative to the Earth, plus then the velocity of the Earth relative to the satellite. Okay, this is my equation that I got to solve for. Now, remember, velocities are vectors, so they have direction too. So don't just find this and add them together and get your answer. It's not that straightforward. Okay, meaning you're saying, oh, look, I got them over here. I got this, and that's great, and that's the velocity of the satellite relative to the Earth. But wait a minute, I need to know the velocity of the Earth relative to the satellite. Oh, so it should just be negative. Okay, this is the velocity of the rivet relative to the Earth. That's what I need, so that's plus. So when I add them together, it's 0. Well, do you really, is it really 0, right? Remember, they're intersecting at 90 degrees to one another. Is the velocity of the rivet relative to the satellite going to be 0? No. It won't be, right? So you have to remember that you're adding vectors. So anytime you're adding vectors, directions are extremely important. So what I'm going to do is create a simple coordinate system. Okay. Now, this is going to be tough to visualize because it's on a two-dimensional page and I'm trying to explain it to you in words and, there's a three-dimensional concept. But think about it this way. All right. Let's just look at it like this. Oh, that was a bad idea. Just look at it like this. Here's the rivet. Okay. We have here them intersecting right at this location, right? One, not at that location, but at either of these two. Okay, let's choose this location right here where they're intersecting. Now notice one of them is going in one way and the other is going in the other, meaning it doesn't look like it in the picture, but remember it has to create a 90-degree angle here. So quite honestly, it doesn't even matter how you orient them on your plane as long as they're 90 degrees relative to one another. And it's totally dependent upon, how I'm visualizing the question here. All right. So whether it's going to be here, and here, or there and here, or whatever the case is, it honestly doesn't matter because it all depends on how I'm framing the question. But what's important is knowing that they are 90 degrees apart. Okay. So let's not belabor the point too much more. Let's plug in, or let's detail the velocity of the rivet relative to the Earth. Now, that's going in a particular direction. Let's say it's going this way. Okay? So this is the velocity of the rivet relative to the Earth. Now, remember, here the velocity of the Earth relative to the satellite will be exactly opposite to the velocity of the satellite relative to the Earth, meaning in terms of direction. But I don't know which is which, right? I mean, they're pointing up or pointing down. It's going to be a little hard to know, but just know that the magnitudes are the same. They're just going to be pointing in opposite direction. It's not important to know which specific direction is pointing in this problem. So don't fret that too much. Just know that they are 90 degrees apart. How do we know that they're 90 degrees apart? Well, that's what it says, right? They're going to intersect at an angle of 90. So since I'm adding these two vectors, right, I have to place the tail of one vector at the tip of the other. This goes way back now, right? So here I have now, let's call this the velocity of the Earth relative to the satellite. And when I add the vectors together, what am I really finding? I'm really finding the resultant, right? I want to know when I take this and add this together, what do I get? Well, in terms of your vector picture, you get this. This should all be review. So this is the velocity of the rivet relative to the satellite. So how do we do it? Right, just Pythagorean's theorem now. Straightforward, nice and easy. Okay, so I know I use red here and this is red. They're not the same thing. So let me just actually, let me erase it. I don't want to confuse you guys because it's confusing me. So this is the velocity of the rivet relative to the satellite. That's the question. So again, just calculate the resultant here. Quick resultant formula, right, will be equal to the square root of the sum of all the x's. So this is the only x. So 7.4 times 10 to the third squared plus, well, that's plus 7.4 times 10 to the third. And that's also squared, okay? Right, because this is the same. They're both equal in magnitudes, right? But they will be opposite. Well, not really opposite, but this you might say, well, wait a minute, Andrew, don't forget the negative. Yeah, if you forget, it's not a big deal, right? Because it's being squared, so don't worry about it. Just calculate it from here, okay? We're going to get the right answer. So where do I want to put it, though? That's the problem. I'll put it right here, okay? So the resultant vector here, which is the same thing as the velocity of the rivet relative to the satellite, is going to be equal to square root of 7.4 times 10 raised, times 10 to the 3 squared, right, plus itself. You could just multiply by 2 squared. And we get a value of about 1.04, 1.05, somewhere around there. 1.05 times 10 raised to the fourth now, right? That's fourth, and that is in meters per second. Okay, so this is the answer. This is the velocity of the rivet relative to the satellite. Okay, 1.05 times 10 to the fourth meters per second. Oh my God, right? This is a long one. So this is B. All right, let's keep it going, guys. Let's keep it going. Letter C. Given the rivet is 3 millimeters in size, how long is its collision with the satellite last? How long does it last? So let's do number C. I'm going to do C at the bottom here, bottom left. All right. So C, basically what we're trying to, notice, remember that we do know the velocity of the rivet relative to the satellite that we just found of 1.05 times 10 to the fourth meters per second. Notice also we know a distance, right, or the size of the rivet here. It's 3 millimeters, right? 3 millimeters. That would be the same thing, and you got to do your conversion here. That would be the same thing as 0.003 meters, okay? And we're looking for time. So hopefully when you look at these three things, it kind of spurs a thought in your mind in terms of what formula to use. Oh, wait a minute, velocity, distance, time, isn't that just this? Yeah, it is, right? That's all it is. So solve this baby for time. Just switch these two variables. Okay, so now we get time is equal to distance over velocity. All we got to do is plug it in now, right? So time is the distance, or 0.003. Sorry for the small writing here, guys, but there's a long problem. There's a lot of work to do. So divided by 1.05 times 10 to the fourth. And I'm going to put the time right above here. All right. So 0.003 divided by 1.05 times 10 to the fourth. And we get a value of 2.86. So 2.86 times 10 raised to the negative 7. And that's in terms of seconds. All right, letter C is done. Let's keep going. Letter D. If its mass is 0.5 grams, what is the average force it exerts on the satellite? This one's a little tough because it seems like it's a little premature in terms of where you guys are in the class, but let's give it a shot. All right. So letter D. I'm going to actually do it this way. What are the units of force? Newtons, right? Now, what is a Newton? Okay, remember F is equal to ma. So if you know this thing is a Newton, well, what is mass measured in? Kilograms. What's acceleration measured in? Meters per second squared. So actually, a Newton is a kilogram meter per second squared. Okay? So this, well, that's just a K. Where's the G? Here's the G, kilogram. Okay? So now, let's see if we can use some of this information to help us. Now, what I want you to do is this. I want you to look at this slightly differently. All right? I want you to look at this in this way. So kilogram times meter, right, divided by second times seconds. Now notice this. What are these units right here? If I were to just look at these two units, meters per second, what is that? Well, that's a velocity value, right? Interesting. So that's a velocity value here. Let me box that. Okay, so this is a velocity value. So maybe, could I rewrite this as saying something like this? Saying something like, this should equal kilogram, which is a mass, right? Multiplied by a velocity. And then what's left is the second, so per time? Could I do that? Yeah, you definitely can. Okay, this is another formula you can use here. You're going to see this in a little bit. Don't worry about names yet. Just, there it is. All right. So, do we know these pieces? Well, yeah, we do, right? We're trying to find if the mass of this rivet, we're trying to find how much force it exerts on the satellite. So we have to take the rivet's mass of 0.5 grams. Now remember, we need it in terms of kilograms. All right, so the mass here is going to be 0.5 grams, but I'm going to do the conversion right away. Okay, just add 3 zeros, to the front part of the 5. So it's 0.0005 kilograms. Take that and then multiply it by the velocity you just found, right? The velocity of what's the important velocity is the velocity of the rivet relative to the satellite. That's the velocity you need because those are the two objects that are coming in contact. So that's the relative velocity that's important. 1.05 times 10 to the 4th. Okay, and then divide that all by the time it took for that collision to occur. And that's what we just found in the prior part, right? 2.86 times 10 raised to the negative 7. And now just calculate it. So this would be the average force, okay? 0.0005 times 1.05 times 10 to the 4th. And divide that now by 2.86 times 10 to the minus 7th. And here we get a value of about, this is about like what do we get here? 1.84 times 10 raised to the 7 times 10 raised to the 7th, and that's in terms of newtons. Okay. All right. So that takes care of D. And now finally, last but not least, letter E. How much energy in joules is generated by the collision? All right. So this one, this one's going to predate what you guys have or what you guys know already. This will be coming up when you start dealing with energy in the energy section. Just know this. I'm going to write letter E right here. Please just know that the kinetic energy is the energy of motion. It has a formula of 1/2 mv squared. Okay. So basically all you need to do, kinetic energy is in terms of joules. So let's just plug this one in. All right. So 1/2 times the mass of the object that's moving, and we already found that to be 0.0005. I'm getting a little crowded here. Let me move this over a little bit. Okay. All right, and then multiply that by the velocity. Remember, the important velocity is the relative velocity between the rivet and the satellite. So 1.05 times 10 raised to the negative 7. No. Times 10 to the 4th squared. A lot of the numbers start getting jumbled, right? So, all right, let's plug this in now. 0.5 times 0.0005 times 1.05 times 10 to the 4th squared. Okay, so we get a value of 2.86 2.76, it looks like. 2.76 times 10 to the times 10 raised to the 4th. And that is in joules. And voila, ladies and gentlemen, there is a nice 5-part question. Hopefully that made some sense. Just, you know, a lot of these concepts are, you know, accumulating on one another. Okay. So what I mean by that is, you know, we need to know how to be able to integrate a lot of these concepts. And that's hence the point of this problem, though I think D and E are a little, you know, difficult given where you might be in the class right now. But you know how to solve it now, so that's what's important. All right, I know you don't want to hear me talk anymore. So thank you guys very much for, you know, tuning in. Appreciate your viewership very much. Please remember to subscribe. That would be awesome. Be much appreciated. And I'll see you in the next video. Take it easy.